Okay, well, thank you all for coming. I want to start off, as every great talk starts off, with an apology, not for my technical issues here, but because I know you're all tired, it's been a long day, you've seen a lot of great talks, and unfortunately, I have another great talk for you, okay? And I've got some really great ideas that get me really excited, a foaming foment. And I'm going to have to just squeeze a little more juice out of these shriveled brains you got. So here, what are we talking about today? Omelets need onions, e-graphs modulo theories via bottom-up e-matching. So what is the motivation? Motivation for this? As we've described multiple times today, AC sucks, right? Okay, so this is sort of the paradox of equality saturation. That one of the great things about equality saturation is that it deals with difficult to orient rules in a declarative way. And sort of canonical examples of difficult to orient rules really are associativity and commutativity, okay? But when you actually go and do this using equality saturation, the e-graph explodes. So here we have the example of x1 plus x2 and so on up to xn. If you fully equality saturate this with respect to the AC rules, you get an exponential number of e-classes, one e-class for every possible subset of those variables, and this thing grows and grows and grows and grows. Okay, but this creates like cognitive dissonance because this is crazy, right? This is what we're doing here doesn't seem that complicated. If I had a problem where I give you two terms, one of which is a reassociation and swapping and jumbling of the other term, if I use this generic method to do it, I'm doing like an exponential search. But the obvious thing to do is I should flatten the two terms, sort all the pieces inside of them, and then check if they're equal. It's a very fast, very simple thing to do. And I mean, it's awesome that equality saturation is this super simple generic mechanism that can handle all sorts of stuff you throw at it. But it's kind of crazy, it feels like, that you're paying all this cost for something that should be easy? Shouldn't it be easy? Okay, what can we do about that? That's the motivation for the idea of e-graphs modulo theories. Can we bake in domain-specific smarts into the e-graph, right? And not just AC, there's other things we might want. We might want polynomials, we might want linear expressions, we might want baked-in notions of sets, and we can encode all these things into the generic e-graph facilities. But we want baked-in notions that do smart stuff and are more efficient things. And there's a spiritual guide for what we're trying to do here that satisfiability modulo theories, SMT, is a super successful paradigm. And what it is it's a bunch of domain-specific smarts about particular theories that are tied together in the center by the fabric of a SAT solver and an e-graph, okay? And what we're doing, is very similar and inspired by a lot of the things that are happening in the SMT world. But we don't really need the SAT solver as much. We have a different problem we're sort of attacking. We're trying to do the simplification problem, the program optimization problem, whereas the SMT solver is really oriented to this backtracking SAT stuff that's happening, to proving things are unsat, to getting particular satisfiable models. So everything in there is engineered to that use case, and can we renegotiate what we're doing and re-emphasize, remix the data structures, remix these ideas. And these are just generic, these are ideas that have been around a long time and are put into a particular form in SMT solvers. But can we take the same sorts of ideas and come up with something reasonable that we can call e-graphs modulo theories? In particular, we want a super strong notion of e-matching. Because it's core to the equality saturation approach is that we're doing e-matching, where that's a little less central to the SMT approach. The central part of the SMT approach is ground stuff without the e-matcher. That's sort of a really nice thing put on top. But when you actually go to try and do this sort of thing, try and think about how could this make any sense at all, the massive e-graph sharing, the thing that makes the e-graph awesome, also makes it super confusing. How do you disentangle the pieces you need to disentangle to actually do this theory-specific reasoning? How do you reach deep down inside of stuff and do this? So it's okay, what do we do? I think there's a generic problem-solving strategy for when things are complicated. You simplify, you simplify, you simplify until basically it's obvious how you're going to do this thing. Then you start adding on complication, right? And I think it's important to note that the e-graph plays multiple roles. And what I wanted to show today is teasing apart these very distinct and I think very separable roles the eGraph is playing. And the equality saturation, the typical equality saturation algorithm, is a particular strategy for combining all these roles, but you can recombine them and use them in different ways. So in particular, eGraphs are term banks. They're things that offer ability to add terms into it, and they hold on to it somehow. They're a thing that you can find terms that like produce a thing. You can give it a pattern of a sort of thing you're looking for, and then it'll return a list of substitutions of like the things that are in the graph that like match that pattern. And then also, crucially, there are quality stores. There are things that you can assert equalities into, and they hold those equalities and compact, with respect to those equalities. So those are like the three main things that eGraphs do. Okay, so focusing on the first one, just adding terms into term banks. To simplify the problem significantly, like if we want eGraphs modulo theories, but just want to focus on adding terms, what we have is term banks modulo theories. Okay, and so how do we support a rigid, baked-in notion of a nice theory in the context of a term bank, of an interning structure, a hash cons? And by nice theories, kind of what I'm alluding to is something that supplies a convergent set of rewrite rules, such that you can apply the rewrite rules or canonization procedure, a rigid baked-in canonization procedure that will give you a canonical form of something that isn't canonical. So it takes this funnel of stuff and it'll give you the tip of the funnel, and it'll give you the same tip every time, no matter where you are in the starting funnel. And one methodology for doing this sort of thing is smart constructors. So here's a very simple example for baking in the notion of x plus 0 rewrites to x. Here's a smart constructor where it just checks if you gave it 0, and it doesn't do, just gives you back x if you did that. But otherwise, it actually does hash cons and creates a new thing inside of the term bank that you can search for, you're going to be able to search for later. And these smart constructors can have more complicated stuff in them. You'll have all sorts of things in them, and they can recursively call each other. And it's an approach that makes sense for like putting things, only the canonical forms, into a hash cons. Okay, so I mean that was a whirlwind, but that kind of gives us a check mark on the first thing. Like we can have a notion of term banks modulo theories. But now we want to think about matching. Like how are we going to do this part? And so the basic issue is that like we've destroyed all the things that were up in the funnel are actually the things we want to match on. And the only thing that's actually materialized inside of our data structures is the very tip of the funnel. Okay, so we have an example like a pattern, x plus 0, like that should match on everything, right? Because like everything is equal to x plus 0. And if we add this particular term, x plus 0 plus y, into our term bank, we'll get that thing inside of our term bank, and there's no zeros in there. So if you do a naive thing that's looking for zeros, a naive pattern matching, you're not going to match on anything. Okay? So I think there's a first intuitive thing that like, okay, well, we just need to like generalize what we're doing in matching. And really this is related to what even the e-matching is happening as inside an eGraph. And so instead of doing like this thing where we're doing just structural looking, every time we look down inside a node, we need to expand into that funnel and look for all the stuff that might work in that funnel as we're breaking into each of these nodes. And the way top-down e-matching works in the context of a term bank is the very first thing you do actually is you scan the entire term bank for a root to start top-down e-matching on. Okay? And then the number of substitutions you're going to get out of this thing depends on the particular theory we're talking about. And every time you go down a node inside of your pattern, you sort of gain a possible theory factor f of the number of substitutions. And these factors are multiplying as you go down the patterns. And we can talk about expanding these things out for multiple different theories. The thing that's like the baseline version of structural matching is like the theory of algebraic data types. You might call that. You might call it not having any theories. Maybe that's another perspective you might have. And the theory factor there, the thing that we're most used to talking about, the thing that happens in most programming languages, the theory factor is 1. But now we're really emphasizing like the equational case, the case where there's theories baked in. Okay, so one example of that is in an eGraph where you have this e-node pattern. You want to see if that e-node pattern is inside of that e-class. So the size of that e-class is the number of possible branching factors that occurs as you traverse down into that pattern. There's multi-set patterns, and there's more than one notion of multi-set pattern, which I think is pretty interesting. And multisets are also interesting. I started talking about associativity and commutativity, and kind of multisets are a way of talking about associativity and commutativity. Multiset, an associative and commutative expression is a multiset of all the leaves that are in that expression. So multiset pattern notion 1 is that we have variables as elements inside of the multiset. And in that case, the number of variables we have inside that pattern, all permutations of that, is the theory factor as we go down there. There's a second notion of multiset pattern, which matches more of our notion of what we typically want when we're talking about AC matching, which is the multiset addition needs to match this other thing. And then the theory factor is the number of partitions, is the number of possibilities we'll get as we go down this thing. And then we get to something very interesting that really, I think, kind of just stops us in our tracks about like, what are we doing? Does what we're doing even make sense? And that's linear patterns, if I'm talking about linear arithmetic. And linear is supposed to mean good. It's supposed to be like the most tractable thing there is, right? And as I've phrased the problem so far, that you need to return like a list or a stream of substitutions of a particular kind, this actually has a theory factor of infinity. Like when you hit this thing, the solutions are x binds to any possible integer z, and then y would bind to any possible integer 42 minus c. And all of those possible combinations are valid substitutions to this problem. Okay, so it's like, what do we do at this point? Well, I guess we must have been asking for the wrong thing. The signature of match must have been wrong. Maybe we should return like a frozen constraint. Maybe we should like go somewhere else into the pattern, hopefully ground x first, and then this becomes like more tractable. You know, there are different possibilities, but I want to talk about a very interesting and like simple, like cutting the Gordian knot kind of possibility of how to deal with this problem. And that's the first key idea of this talk, which is bottom-up e-matching. And really, we've been talking about e-matching over the term bank, not on the term. We reduced in top-down e-matching the problem of matching over the term bank, this second signature, into this first thing, but we don't necessarily have to do that. A lot of our intuition about pattern matching comes from this single term case, which is what happens in most programming languages. And like, you know, people are just sort of used to thinking about like the one problem at a time, but it's very common, like vectorized thinking or thinking in the context of like you're doing a bunch of things at once is like changes how you look at an algorithm. And the algorithm is like brutally simple. Like there's almost no explanation to give because it's so simple. And really what you do is you bind variables by traversing the term bank. Like you decide the set of substitutions I want is ones where variables are bound to something that was inside of the term bank. And in that case, there is like a maximal set of substitutions you could even want to return, a finite maximal set. And you can do this by a brute force like nested for loop thing. So here I have an example of the pattern foo bar of x, y. And in order to bottom-up match this thing, we just guess something for x. We traverse every possible term for x. We guess something for y. We guess every possible term for y. Then we can just look up inside of our term bank, or we can construct this canonized term of foo of bar of x, y, and get the left-hand side. And then the standard strategy in equality saturation is we prune what we consider to be useful equalities based on things that are related to an initial like important term by rewrites or the subterm relationship or combinations of rewrites in the subterm relationship. Because those are the things via congruence closure might like make something interesting happen to our initial target term. Okay, so we can check if it's in the term bank, and then we can construct the right-hand side, and we'll get to it. We can add the equality back into the eGraph. I'll just note this is the like it's as simple as it looks. Like it's kind of like I think the simplicity is sort of part of the greatness of it. And ooh, okay, we're back. Maybe. But there are some optimizations you could put on top of this just to start mentioning a little bit of it. That bar of x doesn't depend on y. You could do early pruning by pushing that bar of x up above the for loop for y. You should also do pruning on what things you're expanding out of in terms. And like you should expand only out of the things that are of the sorts of the variables you're looking for, which is kind of a way of baking in the A-log tutorial yesterday, we're talking about this universe trick of keeping a table that's all the terms that are in a particular sort. Like this is sort of baked into this idea of how you're approaching the problem. And then also, if you can use the tables to sort of prune things that you want to do, this starts to push more and more towards the worst case optimal join style of doing things, just with a very particular ordering of what you're doing. So you can start optimizing in that sense towards the worst case optimal join version of this. But really the punchline here is that bottom-up e-matching plays much, much nicer with theories. Okay? And so to see this, we can talk about the rough asymptotic cost of these different procedures of going about it. The cost of top-down e-matching is you pay a cost t for scanning the entire term bank to find that root term to start top-down e-matching on. So you pay that no matter what. And then every time you expand a theory node, you pay the theory factor f. Okay? But for some theories, if you look at it this way, the theory factor f is infinite. It's just like not even doable. Or it's like some combinatorially large thing that involves a factorial or something. So this can be expensive for very, very deep patterns. The more you're traversing down into the patterns, the worse and worse this gets. Whereas bottom-up e-matching, you're doing this like backwards feeling thing on the outset of like an exponential cost in the number of variables of your patterns scanning over the entire term bank for each of these. So it's exponential in the size of the term bank and the number of variables in your pattern. But notice the theory factor doesn't even show up in this expression because you build the term, you canonize it, use your canonizer, and like you don't have to expand out these things according to the theory expander. And so it changes the incentive structure even of what you're trying to do. Now I paid this I've done this kind of horrible thing to like do this bottom-up e-matching thing, but now every theory I add in, you get the theory for free. It doesn't cost any implementation effort in terms of making a new expander. You have to make a canonizer, and you don't pay the theory factors of expansions when you're doing traversing down through patterns. And so a good example for top-down matching is, or a bad example for top-down matching is a very deep pattern with few variables. You're like paying that cost t no matter what, whereas in bottom-up e-matching pays the cost t to like bind to x, but then it just builds the thing. So that's like a good situation for bottom-up. A very bad situation for bottom-up is tons of variables in a very shallow pattern. That's like not a good situation for bottom-up, but a much better, good situation. You pay very few f's for top-down. And really, of course, like the optimal versions of all these things are going to be mixes of all of it. It's going to be a relational style thing, or you're switching between top-down and bottom-up, or side-to-side. And that strategy has to be able to beat top-down and bottom-up because it includes both of them. But I think bottom-up is really interesting as a point on the Pareto frontier of simplicity and power. And the reason it is so simple and it I think kind of works so well is that bottom-up also grounds really, really fast. It immediately grounds the pattern, whereas top-down delays grounding the pattern as long as possible. Ground is good, unground is bad. That's like a lesson of eGraphs. eGraphs is all about ground terms. It's a lesson from term rewriting. Like all the ground stuff is way, way better behaved than anything with variables in it. And also, in terms of implementation effort, you only need the canonizer to do bottom-up. You don't need to implement a new thing in terms of the expander / unapply. Thank you, Max, for the pointer to the magic word unapply. OK, so we've discussed a version of term banks modular theories where we can add terms, we can match over them. And now I want to talk about the last component where you want to be able to assert new equalities. We only had this rigid notion of rewrites of theories and things. We want to be able to add in these things that we're learning online into the thing. And so we're sort of switching gears a little bit into a true eGraph style thing. So a question to ask, what does a union find really do? What interface does it present? So you have the union find T that has stores all the information of the union find. You have the notion of an ID. And then the union find can tell you if two IDs are equal. It can give you a fresh ID. It can canonize IDs. You can assert equalities using the IDs back into the union find. But not only a union find presents this interface. The interior details of the union find from the perspective of the functioning of the eGraph are largely irrelevant. The fact that their integer IDs doesn't really matter. The way if you implement it as ref cells versus as a vector arena or something, that doesn't matter. Mostly what really matters is this interface. Okay, so that brings us to the second key idea, structured EIDs. EIDs that aren't just bare integers anymore that don't mean anything. And alternative names for this, and I really just can't pick one of them because I like them for different reasons, is semantic EIDs / the really loaded term values, okay? And the reason a like thing that I keep coming back to like foment on is that I really do think e-graphs are well thought of, at least, as models, as like semantic things. And for, in particular, a partial logic with two forms you can assert into it, there's a notion of equality, but also a crucial part of the way we use an e-graph is really, it's like very meaningful whether something is in there or not, whether you like say this term exists or doesn't. So there's some sort of term existence assertion that I think is really like the best fit logic for what an e-graph actually is. Another way to see that e-graphs are models is if you take Z3 and you make uninterpreted functions in an uninterpreted sort, and you ask for a model after asserting a bunch of equality axioms, you'll get back this thing that really is kind of is the e-graph. It gives you a bunch of values and tables, and but it totalizes them, and it doesn't give you the minimal model, which is the thing we kind of want in the equality saturation case. Okay, so we want to have structured EIDs. And what we're going to do is replace the union find with theory-specific extensible canonizers, some of which require a notion of rebuilding, like the e-graph itself. And when it does, the rebuilding very often has the flavor of a ground Knuth-Bendix completion. And ground Knuth-Bendix completions are fairly well behaved compared to the general Knuth-Bendix completion case. In particular, the stock union find can be thought of as uninterpreted values and atomic equations. That's the theory it supports, the theory of uninterpreted values, these things that have no structure to them. And another thing that structured EIDs lets you do is it merges the concepts of containers, primitives, and EIDs. These are notions in egglog where you can have I64s or something, and then but they have to be like totally separate from things that are unionable. But these things start to be able to talk to each other, which is, I think, a useful capability here. Another sort of mantra of the approach is that e-nodes are the like intern things, whereas structured EIDs are like the ephemeral things, the things that you're going to destroy, the things that don't need to be interned, and the things that you want to be able to sort of deeply introspect all at once. So that's again the flavor of the idea. And then I have a pile of examples of things that take this shape. Generalized union finds, these extensible theory canonizers. So the basic version of it, the simplest version of it, is a union find where you have an atomic / uninterpreted structure EIDs that just look like E sub 1. The next version of it that I think is pretty interesting is more like what a union find looks like in Prolog, where you can union like a EID to like a concrete entity, a concrete I64 or a concrete notion of constructor. And I think there is utility in teasing out, even though you can encode constructors as part of the general e-node facilities, I think it's useful to think of it separately because it's like very canonical when something becomes a constructor. It's like, and that immediately lets you talk about disequality. Once you know two things are constructors and different constructors, you know they're never going to be equal unless your theory is inconsistent. And so the way it works is when you have two EIDs that get unioned together, you do the regular union find stuff. If you have a primitive being unioned with an EID, the primitive has to win and become the root. And if you union two compatible constructors with each other, you resolve the union call by unification. You traverse into the children. And so this is a notion of having baked in unification. Something, again, you can encode as rules, but it bakes it into the e-graph as like, oh, this is something really important we actually want. Another notion, and this is, so the top three are sort of the cheapest things you can do that are really kind of easy to just like slot right in there, is the notion of a group action. You can attach every edge in a union find with a group action relating a child to its parent. And so an example of this is a structured EID. Here's the example of using the group of addition with the integers. So you can negate an integer, that's the inverse, and you can chain these things. As you go up the union find, you can add 7 plus 3 plus 4 as you like keep traversing these edges to understand the relationship to the root. And then if you want to compare two things, the invertibility of the group is the thing that lets you turn the comparison to the roots to the comparison to the two leaves. And there's a talk I highly invite people to check out at the PLDI sessions where they call this a labeled union find, and they're using it for program analysis. And an interesting idea that they talk about there is the interaction of this thing with the lattice analyses on the EIDs themselves. So these can talk to each other and inform each other, which I think is a really interesting idea. Okay, next level up in complexity, a really cool thing you'd want is linear expressions, structured EIDs that are linear expressions. So now, like, the things that go in the EID slot are like linear combinations of these base EIDs. And the way you can canonize these things is Gaussian elimination / row echelon forms of matrices. I have an example in the preprint that goes into more detail on this. But if you do once you pick an ordering of your variables in linear algebra, you can make a row echelon form, and that can be seen as a canonizer of linear expressions. It's sort of an interesting, like, reflective kind of thing. I find this too interesting to not note. I don't know what the point of it is, but ground terms themselves have a canonizer, e-graphs. And so your EIDs could themselves be ground terms. You assert them into an inner e-graph. You extract out a canonical form, and that's like the extensible canonizer you could have. I don't know, kind of interesting. Okay, so all these are decidable and cheap. Now we're getting to decidable and expensive. So these still terminate, but like you're paying something here. Starting to be kind of an intense computation you might be paying for. So polynomials also have a notion of an extensible canonizer, and that's the notion of a Grosvenor basis. And so this makes sense from the context of commutative algebra or something, that like if you have a bunch of polynomials that you set to 0, you can convert them into a new set of polynomials that easily lets you canonize other polynomial expressions. And it has some of the flavor, again, of a ground Nuthben's completion, but with all the knowledge about rings just totally baked into the thing. Another very interesting example, getting back to AC, the start of the talk, is ground multisets as structured EIDs. And you can do ground multiset Nuthben's completion. I think it's a pretty straightforward notion of Nuthben's completion. And this is also related to the theory of integer programming in terms of these things called Graver and Hilbert bases, which are in turn related to Grosvenor bases. So it's all sort of in a similar mishmash. Another sort of crazy thing you can kind of do is have your structured EID be SMT terms themselves, and you can canonize them using SMT sweeping, where you just like scan through all sorts of stuff and make a ton of SMT queries asking if these two things are equal. And if they are, now you can like add it into a union find and like replace one with the other one everywhere you see it. Boolean expressions, sometimes you might want to bake in a notion of Booleans, like doing, again, equational rewriting over Boolean algebra axioms is kind of a goofy way of dealing with Booleans, but I mean, it's awesome that the generic facilities deal with it in the super uniform way. But, SAT solvers are amazing, BDDs are super powerful. I think ordered resolution also kind of can make this happen. I'm a little shakier on that part, but I think something does make sense there. Okay, and then we can get to really strong, like undecidable theories, which have capabilities that are really interesting and useful, but the rebuilding of the canonizer is not guaranteed to terminate, okay, or succeed. But there are some caveats there that, like, okay, you could just early stop the rebuilding. Like, in some sense, once it's become undecidable, it's almost as bad. It is as bad as the rules were in the first place. Like, we're all used to the rules don't really terminate either. So maybe you do a little bit of rebuilding of this thing and consider it more like running some of the EQSAT rules, sort of in the same class of thing. But in any case, it might be really useful to bake in associativity, just A. Strange that A is like way more complicated, worse theory than AC, but it is. And that's strings. And string Nuth-Bendix completion with structured EIDs that are sequences of EIDs is a canonizer for that. And rebuilding is running string Nuth-Bendix completion. And I think this is particularly interesting for stateful computation, because stateful computation is about a sequence of things you do. It's not, you don't commute them, generally speaking. And we really want a baked-in notion of stateful computation. I think that's a really intriguing line of thought, or something that supports stateful computation. And then finally, like going all the way sort of a crazy end, like you're putting you could put full Nuth-Bendix completion inside as the rebuilder, as the union find, and then it's almost like what even is the point of the infrastructure of the e-graph outside of that? Because Nuth-Bendix completion is like a super powerful thing of itself. But this is almost, like a thing people want is like a principled way of dealing with destructive rewrite rules. And kind of Nuth-Bendix completion is the principled way of dealing with destructive rewrite rules. Like it's a a saturation technology that can do like reducing computations that destroy uninteresting stuff, but like in a not in a complete way. And then if you let me, I mean, everything I guess is kind of speculative, crazy talk, but like this is some real crazy talk. So there's many things that have been talked about at previous eGraphs or in the community, and I think they kind of fit into this paradigm, but when I've actually tried to do it, I'm like not so sure. So slotted EIDs, I really like that idea. I think like an intrinsic support of variable binding that's principled is like really compelling. And I kind of think it might be something like this, an EID that like has the structure of a very shallow lambda around it. I kind of think that's the right sort of thing. And part of the slotted EID idea has a group union find in it, dealing with permutations of slots. So there's like, it's pretty close to some of these ideas. But when I've actually tried to reconcile them, I haven't actually been able to reconcile like these two things. Colored EIDs is you want a notion of context. So what if we had some notion of gamma attached to every EID? I think that kind of does fit into the general paradigm. Non-commutative rings, I just understand this thing less, but it is sort of a generalization of the Grosvenor basis thing and strings, really. And this is probably going to be super undecidable. And then there's towers of structured EIDs. All of these things are basically containers. And I said like, oh, we put the integer, normal EIDs, like that's the thing they're containing. But you could start to think about like, well, I don't know, what if we just had containers of containers of containers, and then like it bottoms out at like the very base EID. But I think this notion kind of makes sense. I'm a little less sure though. And then a really crazy idea is slotted multisets. I think there's a ground-Bendix completion procedure that kind of makes sense. That combines ground multiset completion with like this slotted thing that sort of deals with the permutation symmetries of the slots. Some related work. This is not the only way to go about things. I think there's a lot of ways to go about things. But some related work to talk about is there's normalized rewriting. There's some papers by Marche from the 90s. And sometimes it feels like the term rewriting people just know everything, but like figuring out what they're saying is a research project unto itself, at least for me. Alt-ergo actually is an SMT solver with a baked-in notion of AC matching, which I think is very interesting. And there's papers about this AC matching technology. Kohler et al. Has like the very pragmatic and I think possibly extremely effective approach to an eGraph modulo theory, which is you extract a term, use your regular term stuff, you assert what you learned back in. Like, maybe that's just the right way to go. It's like, makes a lot of sense. I love the simplicity of it. Like, it seems great. A different approach, like I made generalized EIDs, but another thing you could try and do is generalized e-nodes, where instead of having an ordered children, like requiring that e-nodes have ordered children, they could have containers of children. They could have sets of children, or multi-sets of children, or extensible vectors of children. And that's sort of a different, it's like one-off way of like placing where you want your theory smarts. A thing I've been playing with in some recent blog posts is a brute force SMT eGraph, which is kind of related to the SMT sweeping idea, but it's not exactly built in exactly the same way as some of the ways I've described in this talk. And then I really invite people to check out Pavel's blog posts. He has some really interesting points connecting e-matching to quantifier elimination. I think there's some really interesting ideas in those blog posts. And yeah, so thank you. Again, there's still much to do. This is not meant to close the door by any means on eGraphs modulo theories. It's meant to open the door, open the discussion as like, what other things could we ask of our eGraphs? What other things could be like in there that we want? How would we use them? What would the interface of these things even look like? What should the interfaces be? I think that's the discussion. There's a preprint describing what I've described here and maybe a little bit more. There's a basic prototype of an eGraph modulo theories in my umbrella project, Knuckle Dragger. So there's like docs there, and you can try out a variation of an eGraph modulo theories. Again, different in some respects from what I've shown here, but it is definitely using bottom-up e-matching because like I just think that's a super simple approach and very nice. All right, so thank you.
All right, so we have gone a little bit over time, so I think we should maybe take the questions offline. I really do encourage you to ask Phil about this stuff. There's some really good ideas in here. If you want to see his eyes light up, ask him about Knuckle Dragger. It's a very, very cool project. So yeah, let's take these discussions offline. And that does it for this year's eGraphs. Thank you all for coming. Thank you to Phil and the other presenters for making it such a great day. And yeah, let's continue all these